is where we're going to get started. All right, so 12.47A, we're starting out with this molecule, which is cyclohexene, and then we're going to treat that with ozone, followed by DMS. And then there's a third and fourth step, but why don't we solve this first part? And so this is an ozonolysis where we're going to cleave the alkene to make a dialdehyde. So if we count the number of carbons, 1, 2, 3, 4, 5, 6. At carbons 1 and 6, I'm going to have an aldehyde functional group. So we'll put 1, 2, 3, 4, 5, 6 like this. So I'm going to have an aldehyde here at carbon number 1 and an aldehyde at carbon number 6. And then in the next two steps, I'm going to treat it with number 1 is going to be excess lithium aluminum hydride, which we know can reduce the aldehyde to an alcohol. But of course, I have to treat that with aqueous acid to do the protonation. And so that's going to convert aldehyde to a primary alcohol. Right? That's what's going to happen after steps 1 and 2 in this second part here. So let's write this down. 1, 2, 3, 4, 5, 6. And then we have an alcohol on this end, and we have an alcohol on the opposite end, like that. All right, so there's 12.47A. Let's move on to 12.47D. So this is 12.47D. Oops. And in D, we're starting out with this compound. I've asked this question on a quiz before. So we're starting out with an aldehyde. And then in the first step, we're going to treat that with lithium aluminum hydride. Lithium aluminum hydride, which we know is going to reduce the aldehyde to a primary alcohol. And of course, the second step, we treat that with H3O+. So we're going to draw primary alcohol. So count the carbons carefully. We have 1, 2 carbons coming off of the ring. So we have 1, 2 carbons, and then we draw our primary alcohol. And then in the next step, we're going to treat that with tolusyl chloride and pyridine. And what is that going to do? It's going to make a tosylate, so convert the alcohol into a good leaving group. There's no other part to it than that. Anyhow, here we go. So we have OTS, like that. So there we formed our tosylate. The next one is 12.47E. So 12.47E. And in E, it's a little more interesting. So we're going to take this compound, cyclopentene, and in the first step, we're going to treat it with aqueous acid. Then the next step, we do the Jones reaction. So sodium dichromate, sulfuric acid, and water. Then in the third step, we're going to treat that with phenyl, magnesium, bromide, and then in the last step, we treat that with aqueous acid. So let's start with the first step. If we're going to treat this with aqueous acid, step number 1 with aqueous acid, this is just going to be a Markov-Nikov addition, but there's no differentiation here because the alkene is symmetrical, and so we're going to end up with a secondary alcohol. So we end up forming the secondary alcohol, and then after treating it with the Jones reagent, so our sodium dichromate, sulfuric acid, and water, we oxidize that to the ketone, so we make cyclopentanone is what you would call this compound, and we haven't covered ketone nomenclature yet. The next step, I'm going to draw a partial mechanism for it. We have phenyl, magnesium bromide, and we can treat that as if it's ionic. So what that's going to do is it's going to affect a nucleophilic attack to make an oxonium. So we end up with something that looks like this, where we have, did I say oxonium when I meant an alkoxide? So then we have our phenyl group here. So a phenyl, of course, is an aromatic ring. And then in the last step, we treat that with aqueous acid. And that's just going to do a proton transfer. And so we're going to end up with our final compound, which is going to be this tertiary alcohol. And there we have it. All right, kind of a neat reaction sequence there to make a tertiary alcohol. And then the last two questions that I wanted to take a look at also involved mechanism. So I wanted to look at question 12.51. So this one is just asking for a mechanism in question 12.51. And of course, this is from the Klein 4th edition, our electronic textbook. It says, draw a mechanism and predict the product of the following reaction. And so we have this interesting looking compound like this, where we have this dimethyl group here. And we're going to treat this with excess lithium aluminum hydride. And then in the second step, we're going to work that up with aqueous acid. First question I have for everybody is, could anybody identify the functional group in this compound? And it's not a trick question or anything. Could anybody identify that functional group? It's not an ether, no. It's an ester, right? So when you have an ester in a ring, so this is ester as part of a ring, we call that a lactone. So this is called a lactone. Anyhow, so it's neither here nor there. We learn about lactones later on in the class when we get into the whole chapter on esters or ester chemistry. But yeah, it's an ester. So the reason why we need an ester, why we need excess lithium aluminum hydride is because once we add the first hydride, then we're going to end up having another carbonyl being formed. And so we need to add a second equivalent of hydride to the reaction. So if you're not following with me 100%, let's just start by drawing out the aluminum hydride ion. So I'm just going to pencil it in down here. So we'll draw in aluminum hydride, which looks like this. We have our negative charge, and we're going to have a nucleophilic attack, and we're going to form our alkoxide. So let's draw that intermediate that's formed, and it's going to look something like this, or we have our oxygen or CHEM dimethyl. Now we have our alkoxide like this. You could leave the proton out. I'm going to put it in. But now we are going to lose, right? We're going to lose this oxygen as a leaving group and form a new carbonyl. And again, I mentioned this a couple of lectures ago. The reason why, or probably last class, the reason why this happens is because you form a stable intermediate, which is an aldehyde, after you draw these arrows. So let's take a look, right? If the second curved arrow, if you look very carefully, right, with the second curved arrow, you're breaking the bond between the carbon and the oxygen. Therefore, you're breaking the ring open. So let's draw what that's going to look like. If you count very carefully, look, count 1, 2, 3, 4, 5 carbons, and then we have our oxygen. So let's count. We're going to have a double bond, carbon number 1. So this is number 1 here. And then we have 2, 3, 4, 5. And then we have an oxygen, which is going to have a negative charge on it. And then we have the 2 methyl groups here. So look, I'll number these 2, 3, 4, 5, right? And on carbon 5, we have those 2 methyl groups. But now you have an aldehyde in the molecule, and you know that an aldehyde is going to react with lithium aluminum hydride, isn't it? So we have excess, which means more than, 2 molar equivalents. It means more than enough to reduce anything that can be reduced. And so we have our aluminum hydride ion. We do a nucleophilic attack like this, and we make a second alkoxide. Kind of running out of space here, so I'm going to try to draw a little bit differently here, just so I have some more room. So here's my second hydrogen here. So then I have 1, 2, 3, 4, 5. And here's my 2 oxygen and 2 methyl groups like this. There. So I'm going to number these carbons for you. So I have carbon 1, 2, 3, 4, 5, like that. And then in the last step, I have 2 proton transfers that are going to occur. I don't really have enough room to write them both on here. So I'll just draw one of them, and you can draw the second one in your own time. But all that's going to happen is this guy's going to grab a proton, and then the other oxide or alkoxide is going to grab a second proton. Okay, so we end up protonating both. And so what do we end up with? We end up with something that looks like this. We have 1, 2, 3, 4, 5. We have our CHEM dimethyl. We have an alcohol here. and we have an alcohol here, and that's the final product. So there's quite a few curved arrows in this mechanism, but I think this is a very important mechanism for you to learn, is the reduction of an ester with excess lithium aluminum hydride. And I know that I didn't tell you to do question 12.52, but I would like to take a peek at it. So this is question 12.52, and of course this is Klein 4th edition. And question 12.52 gives us another lactone, except this time it's attached to an aromatic ring. And the question that they ask us is to draw a mechanism for what's going to happen if I treat this with excess methyl magnesium bromide. So I wanted to go over this mechanism with you. And then in the second step, we treat this with aqueous acid. So again, we're treating it with excess methyl magnesium bromide, right? Because we're going to form a stable intermediate that has a carbonyl. If you're not following along, let's take a look here. So we're going to start it with our methyl magnesium bromide. Remember, Grignards are strong bases, but they're also great nucleophiles. And we're going to do a nucleophilic attack like this. And what's the intermediate going to look like? Well, let's draw it. And it is going to look a little something like this, where we have an oxide here, an alkoxide. And now we're going to lose this oxygen. We're going to open the ring. We're going to lose that as a leaving group. So just forgive me, I'm going to move the screen down here to make a little space. And what that's going to look like is this, is we're going to have a phenoxide here. And then if you count the carbons carefully, 1, 2, 3. So we're going to have 1, 2, 3, like that. And on carbon number 2, we're going to have our double bond. Maybe I should draw it like this, 1, 2, 3. There we go. We'll draw it like that. All right, so now a second equivalent of the methyl magnesium bromide is going to be able to attack the ketone that's formed, right? Because we formed a stable intermediate. And so let's take a second equivalent of methyl magnesium bromide, and that's going to do another nucleophilic attack like this. And that's going to give us a tertiary alcohol eventually. So we have our phenoxide here. Oops. Here we go. 1, 2, 3. And now we've got, oops, maybe I'll do it like this. We've got the alkoxide here, and we have another, that's not very pretty, we have another methyl group. I'll draw it like this. There we go. So now we're going to do 2 successive proton transfers in the end to protonate both of those oxygens with a negative charge. And so I'm not going to draw both of them, but the idea is that we take our aqueous acid, our hydronium ion, and this would do a proton transfer like this to protonate here. And then we could also do the same thing with this oxygen here. And we're going to protonate both of those oxygens to give us 2 alcohols. One will be a phenol and the other one will be a tertiary alcohol. And so we end up with a final product that's going to look like this. So here's our phenol. Then we count 1, 2, 3. And there's our extra methyl group. It's going to look like that. So also another very, very important mechanism, the addition of excess Grignard reagent to an ester. So now we've drawn all the mechanisms of all the Grignards and reduction, and we've seen everything in here. And remember, with the oxidation, we actually looked at no mechanisms for that. I showed you a couple of them, but I told you I wouldn't ask you any of the oxidation mechanisms from chapter 12.